Assalamualaikum and a very pleasant morning. I beg to Encik Muhammad Saifuzan and Dr. Waida. I am Muhammad Saidan Bikamuddin, and in this video, I would like to present to you my final year project entitled Analyze of Different Magnet Material of Double Rotor Motor with Bi-directional Features. Okay, this is the overview of this presentation. We will discuss about introduction, motivation, problem statement, objective, scope, literature review, research methodology, and conclusions. Okay, introduction. Okay, this is the example of the common double rotor motor used. Next, this is research motivation. Okay, the motivation that I've come with for this project is that the double rotor motor are commonly used because it has high power, high efficiency, simple rotor structure, and bidirectional features. This is the highlight for this project, bidirectional features. Okay, problem statement. Okay, the problem is that double rotor motor tends to rotate in the same direction. Okay, as we can see from the conventional motor that have been used widely, is that it tends to rotate in one direction only. Okay, the solution for this problem is that the double rotor motor that has been proposed in this project is that it has two different directions. Okay, this is the cross-sectional view and the rotation concept. Okay, from here we can see that it has inner and outer rotor, which will rotate in different directions. For example, the inner rotor will move to the anti-clockwise, and the outer rotor will rotate clockwise. Okay, these types of rotor will be beneficial for conveyor, for production line in the factories. Okay, the objective is that to model the double rotor motor structure by using FEM, known as Ansys Maxwell. Okay, and the second one is to analyze and compare the motor performance in terms of cooling torque, AMF, torque, magnetic flux density in both rotors. Okay, the scope of work. Scope of work is analyze the double rotor motor in terms of cooling torque, AMF, and magnetic flux density that we have measured at the stator in both rotor by using finite element method software known as Ansys Maxwell. Okay, the analysis is then repeated for different types of magnet materials such as NdFeB, SMCO, and ferrite. Okay, the limitation for this project is that we not involved in fabrication and measurement. Okay, this is the motor design used for the analysis. Okay, you can see that we have both rotors, the stators, inner and outer stators, core. Next. Okay, this is the motor specification. Okay, the external inner rotor 56 mm, outer rotor 145 mm, air gap 0.5 mm, coil size 1.25 mm, pole number 20, stator star 18, and type embedded. Okay, the reasons why I chose different types of material for the magnet is that because this is some of the three different types of magnet. Helical, low coercive force but high flux density. Ferrite or ceramic magnet, high coercive force but low flux density. Rare earth magnets such as SMCO and NdFeB, both high in magnetic remnants and high coercive force. Okay, the three types of magnet material that I have chosen is that are ferrite, SMCO, and NdFeB. Okay, these are the literature review. This one is it has applied transmission system at electric vehicles, and then this is for reduce harmonic losses as well as improve integrity. This one is for the proposed comfort, and this is better efficient and practical, especially for emission mode optimization using polyester design. This one is apply for winter generator with a presidential operation. Okay, this is the perimeter of the permanent magnet materials. We can see here. the ceramics, nickel, and rare earth magnets. Okay, the overall methodology. Okay, first start, and then we analyze the motor in terms of cooling torque, back EMF, and magnetic flux density, stator for different current, and number of turns. Then we will repeat the analysis with different magnetic materials such as NdFeB, SMCO, and ferrite. And okay, this is the FEM analysis flowchart. First we start, and then design, and then the design motor in SolidWorks. We will save the design into step file, and then from the step file we will import the step file into the ANSYS Maxwell software, and then we will assign the materials and excitation and boundaries, and then we will do the validation check. If there's error, we will look back at the excitation boundaries, we will check properly, and then if there is no error, we will proceed to the analysis, and then we will get the results, and then we will compare the result for each type of magnet materials. Okay, this is the result for NdFeB magnet. Okay, this is the back EMF that we get from the simulation of NdFeB type of magnet material. And this is the cooling torque that we get. Okay, the max value that the NdFeB type of magnet material can achieve is 11.15 for the outer rotor and 5.4 volts for the inner rotor, and max value for the cooling torque is 0.2 mm for the outer rotor and 0.1 mm for the inner rotor. Okay, this is the single phase back EMF. Okay, I choose the single phase is from this. Okay, I take one example from the 3-phase back EMF for 20 turns of NdFeB magnet, and then I will take one phase, and then I will plot like this for inner and outer rotor, and I will compare for every number of turns. I will, as well as the cooling torque, and then we'll proceed for the torque. Okay, this is the comparison between every number of turn for the torque produced from the simulation. Okay, we can see that here the value is 1.1, and then from here the value will increase as the current increase and the number of turn increase. Okay, the orange one is for the outer torque, and the blue one is for the inner torque. And then we will repeat. Okay, and this is the magnetic flux density that we have measured at the stator. Okay, we can see that from here the magnetic flux density will increase as the current increase, and then at a certain time it will not increase, it will remain the same. This is because at this point the magnetic flux density has reached the saturation level. So even if we increase the number of turns, or if we increase the current, the torque will never rises. The torque will never increase. Okay, and then we will repeat the process for other type of magnet material. Okay, this is for the back EMF, single phase back EMF for SMCO magnet, and the cooling torque for SMCO magnet. And this is the 3-phase inner BEMF, and then this for the outer BEMF, and this is the torque that we have simulated. It is the same. It will increase as the number of turn increase, and when we increase the current, it will increase. Okay. This is also the same when the magnetic flux density achieve the saturation level, it will not increase anymore. Okay, also this is the same ferromagnet. Like 3-phase, and then this is the torque for every number of turns, and this is the magnetic flux density for every number of turns. Okay, the conclusion for this presentation is that each materials have their own advantages and disadvantages. Okay, the higher the torque, the higher the current, the greater the magnetic flux density. Okay, the greater the magnetic flux density, the greater the torque. Okay, the value of torque will not increases even when we increase the number of the current or the number of turns during the saturation level. And the motor design will be beneficial for the application that needed for bi-directional features in the future. Okay, this is my contact info phone number, and this is my email for future reference. Okay, now I will show the simulation part of my project. Okay, first of all, the first thing that I have to find is the back EMF and the cogging torque for this for this model, and I take the 20 turns 0 amps design, and then I will assign the boundaries and excitations for each of the model. Okay, for example, I have assigned all the phases and boundaries, the directions of the magnet movement, and then I will validate check if is there any errors. If there's no error, and then I will run the simulation. Here I will analyze all, and then we will get the results as shown from the presentation earlier. This is the example of the back EMF for this model. Okay, and then after we get this results, I will export the results into a tab file, because if we want to inject the current, we have to import the file. After we have done some calculation, we will replace the tab file into this tab file. For example, like this. I've done some calculation, and then I will save the injected current calculations into this tab file, and then I will export into the simulation. For example, I take for 20 turns 2 amps, and then I will assign I will inject the current from here. For example, if from the previous model, the current we set is 0 ampere. Okay, if we want to inject the current into the model, we have to open the file that we have saved in tab file just now, and we will type like this: pwl underscore periodic ps1 comma time. Okay, after assigning all the phases, we will do the validation check. If there is no error, and we will analyze the simulation just like now, and then we will get the results like this. Sorry. For example, for the dynamic torque. Okay, this is the example that this is the example result that we get from the simulation. This is the inner torque, and this is the outer torque from the injected current. Okay, so from here we can calculate the average value, and then we will insert it we will plot the graph for every simulation. Okay, thank you.